So dear students, welcome to another lecture of basic electrical engineering. In this particular lecture, we will discuss about the speed torque characteristics of a separately excited DC motor. Also, we will discuss the concept of torque in DC motors. Now to start with, as far as the principle of DC motor is concerned, or the principle of motor is concerned, now, it has a very simple principle that when we place a current carrying conductor in the magnetic field, so that current carrying conductor experiences a force, and the direction of that force is given by the Fleming's left hand rule. For example, if you have a magnetic field, let us say the direction of magnetic field is this. So, this is the magnetic field. If we place a conductor in this magnetic field, and let us say this conductor is carrying some current I. So because this is a current carrying conductor, so the current is entering into this conductor from this side, and it is, let us say, coming out from this side. So if you use the Fleming's left hand rule, so as per the Fleming's left hand rule, if we put our middle finger with the direction of the current, first finger with the direction of magnetic field, and thumb gives us the direction of force. So this particular conductor will experience a force, right? And this becomes the base for the electric motor. So whether it is an AC motor or a DC motor, that particular principle remains same in all the motors, right? So only then we get the motor action when we have the current carrying conductor placed in the magnetic field, right? So now let us proceed further. Let us see. Now, as you can see in this figure, now before we go to the torque uh, developed in the DC motors, let us understand how the current carrying conductor experiences a force, and how this direction is taken, how this direction of force which is experienced by the conductor carrying current placed in magnetic field. As you can see here, there are four diagrams A, B, C, D. Now, in this particular diagram, we have the field developed by the poles. So this is, let us say, magnet or electromagnet, whatever. This is another magnet or electromagnet. So we have north pole and south pole facing each other. So the magnetic line of force will emerge from north pole and enter into the south pole. Similarly, we all know that when a conductor carries current, so this is the conductor. When a conductor carries current, so that conductor always have the magnetic field, right? So it carries a magnetic field, and which can be given by right hand thumb rule, right? So for example, there is a conductor like this. If the current in this conductor is this one, right? This is the current, for example. So the current is this one. So if you put the thumb with this one and curl your finger, right? So this thumb will give you, if you put this thumb in the direction of current, right? Thumb in the direction of current. Then these curled fingers will give us the direction of magnetic field. So these curled fingers give direction of magnetic field around the conductor, right? So this is how we can find out. So that means the magnetic line of force are from north to south. The magnetic field is available around a conductor carrying current. Now there are two things which you need to understand. One is the cross and the dot notation. So we need to understand these 2 points, right? Now what does it indicate? Now this indicates that the current in the conductor is entering, and this indicates the current is coming out of the conductor, right? So that means when we have a conductor which carries some current, for example, this is a conductor. Now in this conductor, the current may enter and the current will leave, right? So if you see this end from the front, from the plane of the paper or from the plane of the screen, so since the current is entering here, so this end will be represented as in this way. So this means the current is entering. It is going in to the conductor. It is going into the conductor. And this particular end is represented as circle and a dot. So this dot represents that the current is coming out from this point, right? So whenever you see a plus sign and circled, so understand it that the current is entering at this end of the conductor. And when you see that there is a dot and circled, so understand it as the current is coming out of the conductor. As you can see in these two diagrams, C and D. So we have this conductor, this one. So in this conductor, current is in, right? And in this conductor, the current is out. Okay, so that it is coming out means in cross, the current is going away from us into the conductor. Here in this, the current is coming towards us from the conductor. So this is how you can understand, right? Now when you have to find out the direction of the force on the conductor, right, what will be the direction of force? Because it is very important to understand that how the direction of the force will be taken. Okay, because it is that force which makes the rotor of a motor to rotate. Okay, now as you can see here, apply Fleming's left hand rule, sorry. So using Fleming left hand rule, so if we put the forefinger with the what you say, the direction of this one, and middle finger with the direction of the magnetic field, so thumb will give us the direction of force. So thumb can be taken in this way. This is thumb, this is middle forefinger, and then we have a middle finger, let us say this one. This is the middle finger. So this is in current, this is the field, and this is the force, right? So here the force will be downward. So if you can try it, okay? So you can try it and try to find out where the direction will be. So in this case, the direction of force will be downward. Similarly, if you apply Fleming's left hand rule in this case, this one, so here, as you can see, the current is coming out of the conductor because here we have a dot encircled. So if we place our middle finger towards us, middle finger of left hand towards our face, forefinger, that means the first finger, in the direction of magnetic field. So the thumb will give you the direction of force. So you will always find that your thumb is pointing upward. If you make all these three parts, that is thumb, forefinger, and middle finger, perpendicular to each other, place the middle finger in the direction of current, that is because the direct current is coming out of this conductor. So your middle finger should point you. Then put or place the forefinger, that is first finger, in the direction of magnetic field. Then you will find that your thumb is pointing upward. So that means the direction on this particular conductor will be upward, right? So because in a motor, like if we draw a simple elementary motor, so we have, let us say, a north pole is here, a south pole is here, and we have a coil, right? And then we have some split rings, and then we have brushes, and then we have a supply. So if you see, the current will be flowing like this. So this is, let us say, A, B, and C and D. The current is flowing like this, right? So this is how the current is flowing. Now when it rotates, so the direction is this one. The direction of magnetic field is this one. Now in this particular conductor, the direction is this one, and in this particular conductor, the direction is from D to C. Now here, if you see this, if you see the front view of this particular, so the front view of this would be here. This is B A conductor, so it will be represented as plus and circled because the current is from B to A, this one, and this part is, the current is coming from D to C, so it is coming towards you. If you see this from front, the current is coming towards you, so it is encircled and dot. So current is from D to C, and the magnetic field is this one in both the cases. Magnetic field is this one in both the cases. So that means this particular conductor will experience the force downward, and this will experience the force upward. So that means this particular part AB will go downward, and this will move upward, and its rotation will be anti-clockwise. So this is how it would be rotating, right? So because the conductors work in pair, if one conductor of a pair is having the direction in one side, the another conductor of that pair will have the direction of current in the opposite side, so that the force which is experienced by these conductors will be assisting each other. The force will assist each other, and we get a particular direction of rotation of the motor, right? Now let us see this. So as you can see here in this diagram, so we have north, south. So same thing has been explained here, which I have just explained. So now, so this is the rotor part. which we call as armature. So we have two conductors placed here. So these two are the conductors. So they are being connected back to back from with one another, and their ends are connected to the commutator like this. And then we have the brushes here. So the supply will come and go, enter here, come like this, and here, and like this. So this is how the direction will be. Now, as you can see in this, that here current is in, and here current is out. The field direction is this one, from north to south. So if you apply Fleming's left hand rule here, so the direction on this particular conductor will be upward, and direction on this particular conductor will be downward. In this case, right? And hence it will get a direction, right? It will get a particular direction. Now let us see it in more elaborated way. As you can see here in this particular diagram, this is the armature or rotor, right? These are the conductors. All these are the conductors. These are the conductors. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 conductors. So let us say this conductor is connected to this conductor back to back. It is connected to this, it is connected to this, it is connected to this, it is connected to this. As we cannot see the connection here, but because conductors are always in pair, right? So we have, let us say, 5 pairs here, okay? 5 pairs. Now, if you see in this particular diagram, this plus sign indicates that current is in, and this indicates out. The direction of field is this, that is direction of field is this, like this, like this, like this, radially. The magnetic field is available radially, right? So if we use Fleming's left hand rule, so we will see that this particular conductor will experience torque in this direction. It is in this direction, direction, and these conductors will experience the force in the direction which will assist the rotation. You will never find that the two conductors will have the same direction. No, this is wrong. No, the two conductors will have the direction always opposite, so that they can rotate in a particular direction, and hence in this case the motor will rotate in anti-clockwise, right? So this is how we get the rotation in the motors. Now what is the equation of the torque? Because now this is how the torque is developed in the motor. Now the magnitude of the torque which is developed in each conductor, because the conductors always they are in pair, so in every conductor will have a particular torque. So that is given by BILR Newton meter. So this is the equation for this. So if we have Z number of conductors, so the torque developed by the armature will be the torque developed by each conductor into Z. So this is the total armature torque at the armature, right? Where B is the, let us say, gap density. It is nothing but the flux density. So it is given by phi by A. right? So this is the equation for the this particular parameter, flux density. I is the armature current in one conductor and it is in amperes. Then L is the active length of each conductor. That means, so if we have the magnetic field like this, so we have a coil elementary, let us say. So this is what L is, right? So the part of the conductor which is exposed to the magnetic field, right? So if this is north and south, the direction of magnetic field is this. So the length of the conductor which is exposed to the magnetic field is taken as L. Then R is the radius. Okay, so if we have an armature like this, north, south, so this is the front view, right? So we have some conductors placed on the periphery, right? So this is the direction of magnetic field. So R is nothing but the average value of the distance at which the conductor is placed on the armature periphery, and Z is the total number of conductors. Then uh, this torque is basically expressed in terms of the armature current because of the motor action. Now the motor action is that current carrying conductor placed in magnetic field experiences torque. So that means this torque is based on the armature current. It is based on the magnetic field, that is flux. It is based on the number of poles because magnetic flux is because of poles, right? So we have to express TA in terms of these parameters. Now this is nothing but the armature current. So armature current per parallel path, because we may have a lap wound, okay, a wave wound DC motors. So in lap wound A is equal to P, in wave wound A is equal to 2, right? So per parallel path, this is the amount of current here. So I is equal to IA, which is nothing but armature current, right? Uh, so this is armature current in conductor per path, per parallel path, sorry, right? So we may have either P number of parallel paths or two parallel paths in a DC machine, like, right? So flux density is given by flux per unit area. So the area here is the total area which is exposed to the magnetic field, and because we have a cylindrical shape rotor, okay, so this is the armature. So it is cylindrical shape, armature is cylindrical shape, right? So we have the uh, you know uh, what do you say, the poles like this, okay. So this is a cylindrical shape, it has some radius R, it has some length L, right? So its area which is exposed to the magnetic field, which is exposed to the magnetic field per pole, that means every pole will have some share of the area of the armature, means a particular part of the armature, particular side of the armature will be facing a particular pole, right? And the opposite side will be facing the other pole, right? So the area of cylinder is 2 pi RL divided by P. So this is the net area or cross sectional area of the armature uh, per pole, right? So now we have seen that B is equal to phi by A is equal to this. So B is equal to phi by 2 pi R L divided by P, or B is equal to phi P by 2 pi R L, and I is this one. So we will put this value and this value, both values in this particular equation. So on doing so, what we have got? we have got this equation. So when we substitute the equation of B and I in the equation, TA is equal to BILR, Newton meter. So B we know, we have got I we know, it is IA by A. So this is how we will get the equation. So here L will be cancelled out with L, and we have this equation with us, right? So this is the equation. Now in this equation, if you see, R is cancelled out with R, so we have this one. So now on simplifying this equation, what we have got? We have got K phi IA, because now what is the reason behind this? Because this Z is a constant, right? Now why it is constant? Because for a particular type of DC motor, number of conductors will remain constant. You cannot vary the number of conductors once the armature has been manufactured, created, right? So the number of conductors on that armature will remain same. It is not that you will change the number of conductors. Will you change? No, right? So Z is constant, 2 pi is constant, number of poles, that is number of poles. So for any particular machine, number of poles will remain same. It is the hardware, right? You cannot change the number of poles. Okay. So if there are, it is a four-pole machine, it will remain four-pole machine all the time. If it is a two-pole machine, it will remain two-pole machine. If it is an eight-pole machine, it will remain eight-pole machine. You cannot change the number of poles all of a sudden. Number of parallel path A will be constant, right? P is constant. Okay, so now what we are left with, we left with phi and ia. These are the variables. They are not constant. They are not constant, right? So we can say that for any particular type of DC motor, some parameters are constant and some parameters are variable. So we have written TA is equal to K phi ia Newton meter. So we can say that K is nothing but Zp by 2 pi a. It will be constant for any machine. Now from this equation, what we have understood? We have understood that the torque Ta is proportional to flux, product of flux and Ia. It is proportional to product of flux and armature current. Now let us try to understand the speed torque characteristic of a separately excited DC motor. The purpose of this lecture is to analyze the speed torque characteristics of a separately excited DC motor. Now, a separately excited DC motor, as you can see on the screen, is the one in which the magnetic field system is excited with a separate DC source, right? So the field system is not the part of armature circuit. It is separate from the armature circuit. As you can see in this particular diagram, in this we have a motor in which we have applied a voltage V. The armature current is IA and it is flowing in this way, right? Because of the inherent nature of a DC motor, it will always have an EMF which opposes the supply voltage, and we call this as back EMF. So if you apply KVL in this armature circuit, you will get an equation EB plus IARA minus V is equal to 0. So you can rearrange, you can see here the back EMF direction is this one, voltage direction is this one, both are opposing each other, right? So if you apply KVL, you'll get an equation like this. So let us say this is equation number 1. Then rearranging this equation, we will get V is equal to EB plus IARA, where RA is the armature resistance, right? Now we also know that the back EMF is obtained because of the generator action that occurs in a DC motor when it rotates in the magnetic field, right? So the back EMF is given by the same equation as we have for the generated EMF EG, right? NP5Z upon 60A. Now, among these parameters, Z is a constant value, number of poles is constant, number of parallel paths A is constant, 60 is already a constant value. So that means these many parts, these many components of this equation number 3 are constant, right? So we can write it EB is equal to KE phi into N, and let us say this is equation number 5. Now, if we have to write it in terms of radians, right, instead of RPM, where N is actually RPM and omega is radian per second, right? So if we have to write it in terms of radians per second, so we will use this equation omega is equal to 2 pi n by 60, and we can rearrange this equation, so we will get it is 60 omega divided by 2 pi, right? So we can put it this equation in this one, and we will get equation number 6, where kt is a constant which depends upon some parameters. So if you make this equation 5, so equation 5 is eb is equal to ke and phi, and we have 60 omega by 2 pi. So here K E 60 by 2 pi phi omega. So this is nothing but KT, right? This is another constant value. Okay. Now, now if we substitute the equation 5, as you can see here in equation 5, this one, if we substitute this equation in equation number 2, so we will get a new equation which is equal to V is equal to KE phi n plus IARA. Now we can rearrange this equation to get it in terms of speed and the armature current. So on rearranging, we have got this equation, and simplifying, we have got equation number 7. This is the simplified version of the previous equation, right? Also, we have seen in our previous slide that the torque is given by armature torque is given by a constant into phi into armature current, right? So from here we will get the armature current, which is TA divided by k phi, right? So we will substitute this in equation number 7, right? We will substitute it here, right? Now on substituting, we have got equation number 9. Now this equation 9 can be used to plot speed, torque characteristics of a separately excited DC motor, right? So for this type of motor, we can make use of equation number 9. Now from equation 9, we can develop the graphical relationship between the speed and the torque by keeping some of the parameters as variable, like voltage. We can vary the applied voltage, and we can see that how the speed and torque characteristics going to be changed, right? Similarly, we can change this armature resistance. So Ra is nothing but this is the armature resistance, right? So Ra is armature resistance, V is the applied voltage, and Ta is the armature torque, or simply torque, right? Phi is nothing but flux per pole, and Ke and K are the motor constants. right? So that means we can draw the speed torque characteristics with respect to variable voltage, with respect to variable armature resistance, and with respect to the variable flux also, right? So now let us try to understand this. We will keep the uh, the torque on x-axis and the speed on y-axis. Now, if in this equation n is equal to v by k e phi minus t a by k into k e phi square, and then we have R A, right? So if we take this flux, let V and R A are constant and phi is a variable, right? It is a variable, it varies. So as we can say, if phi increases, this n will decrease. It will decrease basically, right? So this is how we can indicate from this equation. However, because our objective is to find out the characteristic with respect to armature torque, right? So if flux increases, right, and so we will get n decreases. But here, if you see this one, so in this case, we will see that there would be a very little drop, right? So the characteristic characteristics will vary like this. So this is the no load, then there would be some drops like this, right? So if flux will increase, the speed will definitely decrease with increased torque, right? So ta will increase in this case, right? Okay, so that means we are drawing this plotting these characteristics between n and ta in with reference to the flux, variation in flux. So the second thing we can see that this is the case one, right? The second case could be that uh, v and phi are constant, ra is a variable. Now let us see what happens when we vary the armature resistance by keeping voltage and flux constant. And then we will see that what is the how the speed and torque characteristic will change in case of DC motor. So as you can see in this particular diagram here, you can see the graph is been plotted between speed and the torque, armature torque, right? Now, if the armature resistance is zero, if this factor is zero, okay. So if Ra is zero, then N is equal to V by K E phi, simple. So this is going to be the maximum value, right? So if Ra increases from zero to some value, one or two or three or whatever, right? So we will see that this negative part is increasing actually, because phi is constant, v is constant, right? So that means if we increase Ra, so this negative part is increasing. So when this negative part is increasing, so n and ta will have an inverse relationship now. Okay, so they are having an inverse relationship with each other. So as you can see, when we increase the resistance, armature resistance, the speed torque characters will go change in downward direction, right? So here you are getting maximum value. This is, let us say, R A is equal to 1, for example. This is Ra is equal to 2, for example. This is Ra is equal to 3 ohm, for example. So that means as we are increasing the value of Ra, so this factor is going to increase, and when this factor will increase, so N and Ta will have an inverse relationship. So with increase in armature resistance, we have the characteristics in this way. So this is how we'll get the speed torque characteristic. So that means for every increase in the armature resistance, the speed of the DC motor will decrease with the increase in torque, right? Now, the third is that if we keep, so we'll write the equation once again, V upon K E phi minus T A R A divided by K E phi square. Now here if we keep R, A and phi constant and V as variable. That means if we vary the supply voltage, applied voltage in case of DC motor, right? Then what will happen? So you can see here in this diagram, this is the armature torque. So if we decrease the value of V, okay, so let us say V is 0. So in this case, N is equal to minus T A R A divided by K K E phi square. So that means now R A is a constant, phi is a constant. So N is equal to minus some K dash T A. So that means N is proportional to minus T. So they are having an inverse relation, with each other. So that means with increase in speed, that means we will have a negative slope here, negative slope, right? So it is a linear relationship with negative slope. You can see we have a negative slope here, right? So here the voltage is decreasing. So let us increase the voltage. So V is, let us say, 10 volt, for example. So we have N is equal to 10 by K E phi minus T A R A divided by K K E phi square. So now R A K E and phi constant. So we have N is equal to, so this is also constant now. So this is some K double dash, for example, minus. So we have all these parameters constant. So we have, let us say, K dash TA, right? So here now, because we are increasing voltage, so this factor will increase every time, right? Now with increase in armature torque, the speed will decrease. Okay, so we will have a negative slope because this factor will go on, will go to, it will dominate the overall result. Okay, so we will have a negative coefficient of the line. So this is a linear relationship, but we have a negative coefficient, negative slope, right? So now this is how we can draw the speed torque characteristics. So in this particular lecture we have understood this thing only, that how we can get speed torque characteristic of a separately excited DC motor, right. So in a separately excited DC motor, first of all, we derived the relationship between the speed and the torque, right? So on the basis of that, we have got this equation 9. So here we can see the speed torque characteristics for three different parameters, like the applied voltage V, the armature resistance Ra, and the flux phi, right? Okay, so by keeping two at one time constant and one variable, like in the first case we have kept V and Ra constant but flux as variable. In the second case we have kept V and phi as constant but Ra as variable. And in the third case we have kept r and phi constant but v as variable, right? So this is how we can find out the speed torque characteristics and we can draw them. It is very easy. So there is only one equation, which is equation number 9, right? So this is all about today's lecture, and thank you so much.